Part 1 of this exercise asks us to use the plastic model kits to construct all the possible constitutional isomers for C2H6O and then sketch them as Kekule structures. The white bonds are longer than the pink bonds in the model kit because the carbon-to-carbon distance, or in fact carbon-to-oxygen distance, inside a molecule like this of ethanol, these bonds are longer than the carbon-to-hydrogen bonds. This is C2H6O. Carbon catenates, bonds to itself. All the other available valences are occupied. Of course, oxygen has a pair of lone pairs of electrons. There's 2 lone pairs of electrons, giving a bent geometry to the oxygen. This, however, is not the only constitutional isomer. This is an ether. It contains 2 carbons, 6 hydrogens, and an oxygen. All the carbons have 4 bonds. All the hydrogens have 1 bond. And again, I have an oxygen that is bent in geometry and has 2 bonds and 2 lone pairs of electrons. Part 2 of the assignment asks us to use the plastic model kits to construct all the constitutional isomers of C5H12. Well, C5H12 is going to be an alkane, so our simplest alkane is just all 5 carbons stuck together. Longer bonds between the carbons, shorter bonds between the carbons and the hydrogens. C5H12. Okay, let's see how many constitutional isomers we can make. Now, to make a constitutional isomer, I'm going to have to remove a group. So I'm going to take that carbon off, replace that empty valence with a hydrogen, and now I have a 4-carbon chain that's looking for a methyl group to attach to. Okay, still C5H12, 1, 2, 3, 4, 5 carbons, still the same number of hydrogens. Now my longest chain is 4 carbons long, no matter which way I look. 1, 2, 3, 4, 1, 2, 3, 4. So this is a butane with a methyl substituent at the 2. This is 2-methylbutane. To make another constitutional isomer, I would attempt to move the methyl substituent to another place. Now remember, you can't move it to any of the terminal carbons because that would just make the chain long again and go back up to 5. So here's another butane. Perhaps this one is 3-methylbutane. 1, 2, 3 with the methyl here. But no, 1, 2, 3, 4. This is also 2-methylbutane. So when we work through a systematic process of doing this and we get to our first duplicate, that's a sign that there are no more 4-carbon chains left available to us. Let's see if there are any 3-carbon chains available. If I add one of the methyls to carbon number 2, knowing that I can't add the methyls to any of the terminal ends, I'm going to make this molecule. Again, it is 5 carbons, 12 hydrogens. My longest chain is only 3 carbons long. So whichever carbon we identify as being carbon number 2, both methyls are attached to carbon number 2. So this is 2,2-dimethyl propane. Sketch all of these as Kekulé structures. The third part of the assignment asks for something different. It's no longer asking for constitutional isomers, it's now asking for stereoisomers. Show all the stereoisomers of 2,3-butane-diol. So here is bute, 4 carbons in a chain. It's an ane, only single bonds, and it has 2 alcohol groups, so it is a diol. Those alcohols are at carbon number 2 and carbon number 3. So this is 2,3-butane-diol. But as the question suggests, it's not the only stereoisomer. If we look at this carbon, carbon number 2, carbon number 2 is chiral. It's bonded to an alcohol, to a hydrogen, to a methyl, and then to this ethanolic group right here. That's 4 different groups. And carbon number 3 is also bonded to 4 different groups. So this molecule has 2 chirality centers. Its mirror image is this molecule. And if we try to make them superimposable, we fail. These are individual enantiomers of one another. They're enantiomers because they are mirror images and they are non-superimposable. So if this were an R, this would be the S. If this were an R, this would be the S. If that was an R and an S, this would be an S and an R. The configuration, the absolute configuration or stereochemistry at each of these carbons is the inverse of each other. But it turns out these are not the only 2 isomers. This is also an isomer. And it has a mirror image that looks like this. Now this is a very special case because this molecule is symmetrical. The left-hand side and the right-hand side of this molecule, if you split it right down the middle, it has a mirror plane. And anything that has a plane of symmetry, its mirror image turns out to be itself. So in this case, the mirror image of the molecule on the left is the molecule on the right. Now we cannot ignore that these are actual stereocenters, so we invent a new word. These are meso compounds, that they are stereocenters, but that their mirror image is themselves. So technically there are 4 stereocenters, there are 4 stereoisomers for this named molecule, but 2 of them are the same, 2 of them are meso. Part 4 of the assignment asks us to use the Spartan software to sketch CHBrClI to look at that molecule in 3 dimensions, determine whether it is the R enantiomer or the S enantiomer, and then to identify the bond lengths and angles within the molecule. So I'm going to select a carbon to be my central atom, and I'm going to draw 4 bonds to it, and then I'm going to switch those out, that this one can be a hydrogen and a chlorine and a bromine and an iodine. Okay, I'm going to click over to the three-dimensional view, and this is the molecule that I have sketched. You can see that the carbon to hydrogen bond is very, very small, and that the carbon to chlorine bond is much longer. The carbon to bromine bond is much longer in itself. And then the carbon to iodine bond is very, very long. So I'm going to do a couple of things here. I just minimized the structure, so it has idealized the bond lengths and angles, and in doing so, it has given this a name and identified that the absolute configuration at that stereocenter is the R isomer. I can do a couple of other things. This is a space filling representation that shows how much each of those atoms actually occupies space. And you can see that the iodine there in purple is huge, and the bromine in red and the chlorine in green taking up significantly more space than a carbon to hydrogen bond right here. Okay, the other thing that we can do is, on the information page, is I can find some distances. The distance from a carbon to a hydrogen is listed as 1.08 angstroms. An angstrom is 10 to the negative 10 meters. Now that's not an SI unit of distance. It is 100 picometers. It turns out that angstroms are used by X-ray crystallographers because that is the length of an X-ray, but it is not a unit that is widely adopted outside of crystallography. Okay, let's pick a couple of other. So the distance between the chlorine and the carbon is 1.77 angstroms. 1.77 times 10 to the negative 10. The distance between the carbon and the bromine is 1.96. So at this point, that bond length is twice as large as the bond length of the hydrogen. And then finally, the length of the bond between carbon and iodine is 2.17 angstroms. Okay, let's look at some angles. I can either pick out two bonds or pick out three atoms and find what the angle is between those atoms. So the angle between the hydrogen, the carbon, and the chlorine is 108.1. That's squeezed in from the ideal value of 109.5. It's going to be squeezed in because the iodine and the bromine are going to be taking up more space. So if we look at the angle between the iodine and the bromine, that angle is 112.3. That's just sterics. That's the size of those groups pushing the bonds apart. Part 5 asks us to sketch butane, look at the molecule in 3 dimensions, and then look at the molecule the way that you would observe a Newman projection and see if we can tell any difference in the repulsive energies between the staggered anti and the gauche conformers. So I'm going to pick out carbon and just build 3 bonds, 4 atoms, all carbons. The software knows that if I don't add anything else to this molecule, that everything else is a hydrogen. So here is butane, C4H10, and I can minimize that, and it tells me this is N-butane, N for normal or neo, just means all in a chain. Okay, let's see if rotating this around, I can look at this as if it were a Newman projection. So carbon 2 and carbon 3 have just lined up. And when I pressed the energy minimization and it gave me the name, it put this molecule in its most stable conformation, which is staggered anti. Everything in this molecule is staggered. Okay, let's see if we can tell the difference in a couple of different conformations. So in this top left, I have an icon that I'm going to pick out, and it's going to show me some relative energies. Here at the bottom is the conformer that it has picked, and I have a red line there. And if I pick another one at higher energy, this is the staggered gauche conformer, and it is 3.3 kilojoules per mole higher in energy than the staggered anti conformer. Part 5b asks us to do the same manipulations, but using 1,2-dichloroethane. So if I pick carbon, I only need 2 carbons, and then I'm going to put a bond to chlorine at carbon number 1 and carbon number 2. Not going to write the other hydrogens in, not going to force a stereochemistry, which I could do by using the wedged and hatched lines. Just going to let the computer do this for me. Okay, so here is the molecule that it has come up with. Going to energy minimize that, and it automatically has made this 1,2-dichloromethane adopt the staggered anti conformation. And again, we could go back to the space filling diagram right here and show that those chlorines really need to be as far away from each other as you can possibly put them. Chlorines are significantly larger and more repulsive than hydrogens. Okay, let's look at some other conformers. So the staggered anti is here, and its staggered gauche isomer, conformer, is now 5.2 kilojoules per mole higher in energy than the anti-periplanar conformer. So the additional repulsion between those chlorines makes the energy gap larger. Part 5c asks us to look at 2,5-dimethylhexane. One, two, three, four, five, 6 carbons in a chain. There's the hexane, and then a methyl at the 2 and a methyl at the 5. This molecule right here. Let's minimize that. And it rewards us by telling us the correct name, so we know that we've got our structure correctly. Now there's multiple bonds that I could look down, but the interesting one is going to be the one in the middle. right here, these two carbons, because between that carbon and this carbon, I have all of this steric repulsion swinging about, ready to knock into the same equivalent group on the other side. These two groups are really going to want to be away from each other. So when I minimize the molecule, it puts them sufficiently apart like this. Let's go look at some conformations. This is going to be the staggered anti. This is our lowest conformational energy. Okay, going to make these two carbons line up. Those two carbons have now lined up, and the big isopropyl group at the bottom and the big isopropyl group at the top are almost 180 degrees apart from each other. If I scan through some of these other available conformations, let's see what we get. That is also something that we would probably call staggered anti. It's just a little bit different in terms of what the ends of the chain are doing. But now this one is gauche. These are the two carbons that I'm most interested in. And if I get those to line up like in a Newman projection, I have my other groups around it. The difference here is 1.6 kilojoules per mole. And as we flip through, we can see that we really want to avoid having these alkyl groups approach each other. So this one, which is somewhere slightly between eclipsed and gauche, is a whopping 16.9 kilojoules in energy higher than the anti-periplanar one, the staggered anti. Question 6 on the list asks us to sketch cis 1-ethyl 2-methyl cyclohexane and to minimize the structure and to see what effect a ring flip has on the energy of the conformation. So I'm going to I could pick out individual carbons and draw them, or I can just cheat and draw a ring. And then I'm going to draw a methyl at a position, and then one position away from it, draw an ethyl. So this is 1-ethyl 2-methyl. And it specifically has asked me to make this molecule be the cis stereoisomer, which means both of these substituents are on the same face of the molecule. So I'm going to look at this in 3 dimensions and perform a minimization. It tells me this is indeed cis 1-ethyl 2-methyl cyclohexane. So I've got this one right. I'm going to simplify this molecule as just the stick figure. Now we can see the ring, and then there's a methyl substituent and an ethyl substituent. They're both on the same face of the ring, but the ethyl is clearly in an equatorial position, and the methyl is in an axial position, where we would have expected it to be, because we were told the larger the group, the more its desire to be in an equatorial position. Okay, let's look at some conformational analysis of this. My lowest energy molecule is this one, with the ethyl in the equatorial. If I perform a flip on this ring so that it is still a chair, it has to be the ball and stick actually under the conformational menu. I can't go back to just the stick figure. So this is still a chair. You can see the undulation here. But now my ethyl is in an axial position and the methyl is equatorial. So this is flipped and my once equatorial ethyl has moved up to an axial position. This is 2.6 kilojoules in energy higher in energy. Higher energy means less stable. These are the 6 things that you were asked to examine on the worksheet.